I saw this SQL performance tip online that says filter early, join later. Sounds smart, right? Well, here's why this is completely wrong with data to prove it. I was reading some articles on Medium when I ran into this article claiming how to get 80-something performance improvement on your SQL, and it contained a bunch of performance tips inside, and most of them were actually good, and the article had something like 700 reactions, which is pretty decent for a Medium article. Now, one of these tips, which you're seeing on the screen, caught my attention, and I was like, wait a moment, this doesn't really make sense. So the claim is you should filter early and join later to get a performance improvement. So the claim goes that they had a big query where they were joining 3 to 4 tables and then filtering them, and this was causing more rows to be returned than needed. There's a before and after example, which is supposedly better, and what we have is a subquery selecting the data from the orders table and filtering it before applying the join. And the result should be that the database filtered a smaller table first and then did the join, and this saves us time and memory and gives us better performance. But this is absolute crap. So let's actually take a step back and try to understand why this is pointless advice, and you are just better off writing the original query and letting the database decide how to process it. So first things first, we're going to need a database. I'm going to run Postgres locally in a Docker container, and I'm going to execute this command. And now if I open up Docker Desktop, I should be able to see my test database running locally, and if I connect to it on port 5432, I should be able to see my database from something like dbeaver. Now right now, this database doesn't have any tables inside, but we're going to fix this. And to do this, I'm going to create 2 tables, users and orders, like in the example from the article, but I'm going to use a really cool new feature that we're getting in .NET 10, which is running C# files as scripts. So let me walk you through how we're going to seed the data that we're going to be using to demonstrate why the advice from the start of the article is absolute crap. So this is the syntax that you can use to write C# scripts, and you can reference NuGet packages inside of your script by using a hashtag followed by a colon. Then you write package and specify your NuGet package name, and then you can also specify which version of the NuGet package you want to use. And that's it. There's no CSproj file, just a simple C# file with a CS extension, and you can write your program inside. Now what I'm going to do next is import some using statements that I'm going to need for my script, and I'll start by defining a connection string, which is going to allow me to connect to the Postgres instance that I have running locally. And finally, I can open a database connection by instantiating a new MPG SQL connection and passing it a connection string. Then I'm going to open the connection string, and of course I'm going to create a database transaction. So inside of this transaction, I want to do a couple of things. First, I want to initialize my database tables. These are going to be the users and the orders tables, and I want to create them if they don't exist. They're going to be very simple, just an integer for the ID, and then a name for the user, a user ID reference for the order, which is also going to be a foreign key, and then a total value, which I'm going to use for my filter. Then I'm going to insert the users for my tests, and let's say I want to insert 10,000 users. Now don't pay too much attention to the code that's inside of the script. I just vibe coded this using ChatGPT to get something working quickly, but I think it's really awesome that we have this capability in C# now. So what I'm doing here is executing an insert statement with SQL. I'm inserting into the users table, specifying the name column and providing the name as a parameter. This is an extension method from Dapper, and I'm just giving the user a name user and then the index of the current user. And every 1000 users, I'm printing a statement. Then we're going to insert the orders, and I'm going to initialize a new random object, which I'm going to use to randomize the order total. So let's say for each of my 10,000 users, I'm going to generate an insert statement, and I'm going to do this in batches just to make this faster, and I want each of my users to have 500 orders. So that should give me around 5 million orders inside of my database, which should be sufficient enough for us to see a performance impact when filtering the data. What I'm doing here is constructing an insert into query, and I'm going to provide multiple values by appending them using this string builder object. And finally, I'm going to materialize the entire query, which is going to insert 500 orders at once. So finally, after this completes, we're going to commit our database transaction, and this completes my seed script. So how do we actually run this? Well, I'm going to open up a terminal, which should be pointed to where your C# file is. And then you can just say .NET run and specify the name of your file. So I'll say .NET run cdata.cs. So let's go ahead and click enter. And then this is going to build my file. You can see that this already completes and is going to kick off my script. So you can see we already inserted 10,000 users and we're currently inserting the orders. If I jump into the Beaver while this is running and refresh the tables, you can see that there are no tables inside. And this is because I have a database transaction wrapped around all of these operations and none of them are going to be visible until the transaction completes. So now that my script has finalized, we should see the users and orders table in our database. And if I open them, you can see that I have some data inside. So now we can finally test our so-called performance tip to see if it makes a difference. So let me write some SQL. And here's the first query that I want to run. Let's say we want to select the users and the orders where the order total is greater than 500. If I increase the number, this is just going to reduce the overall number of orders that we're going to return. Now, if I execute this, I get a bunch of results back, and this completes pretty quickly. Now, if we want to see what's actually happening under the hood, I have to run explain analyze. And if I do this, I can see what the query plan is for this query. So we're not going to dive into this just yet. Let's also take a look at the second so-called improved query, but mind you that this one takes about 400 milliseconds to complete. So I'm going to paste in the improved query, which should give us a performance improvement. And the supposed reason for this is because we are selecting from the orders table and filtering it to only fetch the orders where the order total is greater than 900. And after we've completed this filtering, we're going to then join on the users table and select everything from that. Now, if I execute this, we actually do get the same result back. So this shouldn't be surprising. But if I do an explain analyze, you should be able to see that this also takes around 400 milliseconds. So what gives? So let's actually spend a moment to discuss the query plan. And I'm going to first analyze the original SQL query. I'm going to highlight this operation here, which is a sequential scan of the orders table, filtering out the orders where the total is greater than 900. So you can see this operation here, and notice that it's on the same level as the next operation, which is constructing a hash table from the records in the users table, which are obtained using a sequential scan on the users table. So once we have all of this, we perform a hash join on this condition, and this gives us our result set. So let's reiterate again. We're doing a sequential scan on the orders table, filtering out the orders based on our condition, and then we're also doing a sequential scan on the users table, creating a hash table, and then doing a hash join. So now let's look at the query plan for the optimized query, and you can see that it's the same exact thing. A sequential scan on the orders table, filtering out the rows where the order total is greater than 900, and then the same thing, a sequential scan on the users table, constructing a hash table and doing a hash join. So what we can conclude from this is that these two queries are functionally identical, with the second query just being more complex to read. We have a subquery that we have to figure out, and then we're joining on the results of this subquery to obtain our final results. Now, the reason this is happening is because Postgres, as well as most modern SQL databases, use a cost-based query optimizer. And what this does under the hood is it takes your query, it parses it to make sure the syntax is correct, and then it's also going to rewrite your query in a format that is most optimal. Finally, it's going to figure out what is the ideal execution plan, for example, looking at which indexes you have in your database, looking at your database statistics, and it takes all of this information and it looks at a bunch of query plans, ranking them by cost, and it picks the query plan that costs the least to execute, meaning it's going to be the fastest. Now, all of this happens automatically without you having to do anything to your query. This is the beauty of cost-based query optimizers. So everything that's achieved by the so-called performance tip is just making your query harder to read. The so-called optimization, where we filter out the orders and then do a join, is automatically done by the query optimizer, as you can see here. So just write your queries how you normally would and let the database take care of how it's going to be executed. Now, there is a way to force Postgres to do what the supposed tip is actually suggesting it to do, and that is to really filter out these rows and only then perform the join. So that would look something like this, using a common table expression, where I'm saying select star from orders where the order total is greater than some number, let's say 900 as in the example above. You can think of this as a temporary table that only exists for one query. Let's say I'm defining a filtered orders common table expression, then I can use this to join on the users. And this will force the evaluation of the common table expression first before performing the join. So if I were to run an explain analyze on this query, let's see what the results would be. And you can see that the query plan is basically the same. This is because from Postgres 12 and up, this can be inline, so it's just going to be identical to the query that we wrote before, but you can also force the common table expression to be materialized before being used in the outer join, and then this is going to behave slightly different. You can see we're getting a different query plan and the performance is slightly worse. Now this becomes even more prominent if I alter the filter to return more rows than should be the case. And you can see that in this case, the execution time is 1.3 seconds, whereas if I were to run our original query with the same filter, the execution time is significantly slower at around 800 milliseconds, so just something to keep in mind. One more thing I wanted to mention is EF Core raw SQL queries, because I remember people asking me about this, and this was a feature that was added in EF Core 7, and it allows you to use your database context to write raw SQL queries and return non-entity types. This would make it on par with what Dapper allows you to do. Now, what's interesting is that you can compose this with LINQ, so I can write a SQL query and then chain a call to a where statement and apply an additional filter, and this would produce a database query like this, which doesn't seem optimal, and from a readability perspective it's definitely not, but as you just saw, this type of query is probably going to be inlined when we actually execute it in the database, so it won't really affect our performance. If you enjoyed this video, make sure to smash the like button on your way out, and let me know in the comments if I should do more SQL optimization videos like this one. Check out my courses if you want to improve your software architecture skills, and until next time, stay awesome.